Good day, ladies and gentlemen. We are welcome to our lecture of Digital Electronics 2, CMEN405, and this is our lecture number 3, part 2. Without waste of time, we go straight to the first item of this lecture, which is digital counters. As their name implies, they are digital devices that are used for counting by following a particular sequence, and their inputs that drives them to operate should either be external source, or sometimes they can be from the clock driving the entire counter. And of course, these digital counters, they are very common devices in digital systems like computer and similar devices, and they are of different types depending on the nature of their operation. And we basically have binary counter, modular counter, we have up counter, we have down counter, and we have combination of up and down counter. So we go straight to the first one, which is binary counter. And this binary counter is any counter that follows binary sequence. For instance, if you have an n-bit counter, it can count from 0 up to 2 raised to power n minus 1. Let us take, for example, our n is equal to 3. 2 raised to power 3 should be 8. 8 minus 1 should be 7, meaning it should count from 0 up to 7. And these binary counters, they are fabricated using flip-flops, and the commonly used flip-flops are either T flip-flop or JK flip-flop. In a situation where JK flip-flop is used, the J and K are connected together. And if you can remember our part 1 of this lecture, we said wherever J and K are connected together, it changes the flip-flop into T type. And also we should know that whenever we are designing n bits counter, we have to use n flip-flops, because we established that each flip-flop has the capacity of single bit. And if we want to design these binary counters, the first thing we do is to develop what we call excitation table of the flip-flops. And how do we do that? The excitation table has 3 segments. The first one gives the present state, and the second segment gives the next state of the system, and the third segment is for the inputs of our flip-flops. And let us take a typical example. Supposing we want to design a 3-bit binary counter, we take x2, x1, and x0 to be our bits, and this is the first segment, which we call present states. With 3 bits, it follows a normal binary sequence 000, 001 up to 111. Then the second segment is what we call the next state. It is also containing x2, x1, and x0. But how do we come up with this? Whatever is the value of the binary in the present state, we increase it by 1 in the next state. For instance, here 000 is equivalent to decimal 0, so here in the next state we should put 001, which is equivalent to 1 in decimal. When we come to the second row in the present state 001, so in the next state we should have 010, which is equivalent to 2, until when our present state reach the maximum value 111, then our next state should now reset to the initial value, which is 000. Okay, so the next thing is, how do we get our entries for these flip-flops? Because we said we are using T flip-flop, and this is T2, T1, and T0. So the way we find the values of these T's is, for example, if we are looking at this T2, for us to get its value, we compare the x2 in the present state and x2 in the next state, and see if they are of the same type, that is, if they are both 00 or if they are both 11, so our corresponding T should be 0. But whenever they are different, that is, one is 1, the other one is 0, then our corresponding T should be 1. let us take for example here, my present state x2 is 0, the next state is also 0, so they are the same. My t2 should be 0. If you look at the second one, x2 is 0, and here in the next one, x2 is 0, we put 0 for the t. The third one, x2 is 0, x2 is 0, and our corresponding t2 should be 0. But if you look at the fourth one, my x2 in the present state is 0, but it is equal to 1 in the next state. So for this, they are different, and we put 1 on that. We continue like that. For instance, if you look at this one, I have 1 for the present state, and I have 1 for the next state. Therefore, my x2 should be 0, because 1 1 gives 0, 0 0 gives 0. Only when we have different, that is 0 and 1, we have 1. Look at, for example, the last one here is 1, and the corresponding in the next state is 0. They are different, then my corresponding t2 should be 1. So to find t1, I will compare x1 in the present state and x1 in the next state. To find t0, I compare x0 in the present state and x0 in the next state, and whenever they are the same, 0. If they are different, 1. So after understanding this, the next thing we do is to derive the expressions for this t2, t1, and t0 to the Boolean function. And how do we do it? We use a counter map. For instance, for t2, I have only 2 places where the value is 1, this place and the last one. And when this is 0, what is the corresponding value? In the present state, we have 0 0 0 1 1, and when it is 1 here, the corresponding value is 1 1 1, which means whenever we are trying to find the Boolean function of this, we consider the present state. And this is the Boolean table, the Kano map for t2, where I have only 2 ones. Combining them will give me x1 x0. And if you go back to that of t1, I have 4 places with 1, here, 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 and here, 4 of them. And if you plot it on the Kano map, we have this, and this is the simplified function. Then if you go to t0, everything is 1, therefore my Kano map should contain all ones, and this is the corresponding t0, which is 1. Now, after obtaining this, the next thing we should do is to come and draw our logic diagram of the binary counter, and we are going to use 3 flip-flops, and they are of t types. So this is the first one, t0, this is the second one, t1, this is the last one, t2. Now, what is the input to my t0? Look at this function, t0 is equal to 1, so I apply logic 1 to it. What is the input to t1? Is x0, so I'll go and tap the output of this t0, which is x0, to enter t1. And what is the input to t2? Is product of x1 and x0, so I'll bring this x0 and x1, pass them through an AND gate, and finally they will enter the t2. This is how we draw our logic diagram of binary counter. The next thing is modular n counter. This modular n counter is any binary counter that goes through repeated sequence of n counts. For instance, if I say modulo 5, I want it to to go through 5 different stages, maybe from 0, 1, 2, 3, and 4. This will give me my 5 stages. So, for instance, if you look at the binary counter we just finished, it is having how many bits? 3, and we have established that it counts from 0 to 7, and you have how many states here? 8. So therefore we can call this binary counter modulo 8 counter. And also, if you design a BCD counter, that is binary coded decimal, that will count from 0 to 9, counting with 0 to 9 you have up to 10, therefore we call it modulo 10 counter. Now, supposing you want to design a modulo 10 counter, how do we go about doing that? We just try to write the corresponding binary value of this 10, and we have established that it is going to count from 0, which is 0 0 0 0, and it will terminate at 9 1 0 0 1. Okay, So now we say, since the maximum value is 9 and it is made up of 4 bits, then we use 4 flip-flops to design modulo 10 counter. And also, supposing you want to design modulo 3 counter, that is a counter that will count from 0 to 2, 0, 1 and 2. That's 3 states. So this one, you know, it will start from 0, 0 and it will terminate at 1, 0, which is equivalent to our 2 in decimal. So seeing this, modulo 3 counter needs only 2 flip-flops. Now let us assume that we are asked to design modulo 10 counter. As we have shown, it will count from 0, 0, 0 and terminate at 1, 0, 0, 1, which is 10 different states. And as I've said, it has 4 bits, therefore I'm going to use 4 flip-flops. But each flip-flop must have a clear input, clear terminal. And in order to make sure that when it counts from 0, it stops from this without passing, we use a NAND gate. This NAND gate is used for clearing everything to 0 when it passes the maximum required state. For instance, you know, in binary, after having 1, 0, 0, 1, the next thing you should have should be 1, 0, 1, 0, but we don't need it. So it should be our clearing point. And if you look at this one, I can call this last bit Q0, this one Q1, this one Q2, and the last one Q3. And you can see it is under Q3 and Q1 that I have ones. So these 2 ones, they should serve as the inputs to the NAND gates, so that whenever it senses that the 2 of them are ones, it will clear everything. This is the logic diagram. For you to do this, we normally use JK flip-flop, but as a rule, the J and the K are always connected to logic 1 permanently. So you draw your 4 flip-flops, this one, this one, this one, and this 4 of them, and all their J and K's, you connect logic 1 to them. The next thing is, the external clock that drives the system should be the input to the clock pulses of the Q0, while the output of the Q0 should be the clock to the Q1. The output of Q1 should be the clock to the Q2, and the output of Q2 should be clock to the Q3. Then the output Q3, you tap it and place it here. Then Q2 also, you tap it and place it here. The same thing with Q1 and Q0. See the outputs here. Now we said the reset points is when we have 1, 0, 1, 0. And as I have said, this is my Q0, this is Q1, this is Q2, and this is Q3. So the points where we have ones are under Q3 and Q1. Then I'll go and tap from those 2, that is from Q3 to serve as input to my NAND gate, then Q1 to serve as input to my NAND gate. Then the output of this NAND gate should be connected to the clear terminals of all the flip-flops, so that whenever it senses Q3 and Q1 equal to 1, it will clear everything. Then it will start from 0, 0 up to 9. Then when it senses the 1, 1, it will clear again. Now the second example here is if we want to design modulo 3 counter. As we have said, modulo 3 counter should count from 0, 0 and terminate at 1, 0, which is equivalent to 2. But you know, after 1, 0, we have 1, 1. So the first information we got from here is that we need only 2 flip-flops, because modulo 3 counter has only 2 bits. So this is my flip-flop number 1 and this is number 2. As usual, the G and K connected to logic 1, and external clock should drive this one. The output of this should serve as clock to this, and I tap my Q0, Q1 and Q0 here. Now we said this is our reset point. That's the point we want the counter to clear 1, 1, then, which means it is from Q1 and what, Q0. All of them will enter here, and their output should go to our clear terminal that will reset them whenever both of them are equal to 1. So the next thing is UpDown counter. The up counter is a digital counter that can count from the lowest value to the highest value. For instance, the 3-bit counter we have seen, it counts from 000 up to 111. So it is increasing from the minimum to the maximum. That is why we call it up counter. And the down counter is opposite of the up counter. Is the one that will now count from the maximum, that's the highest, to the lowest. For instance, for this 3-bit counter, if it can count from 111 and terminate at 000, we call it down counter. And for us to design up counter or down counter, we still use our JK flip-flops. And this is how the diagram should be. My external count enable, that's the pulses that drive the system. They should first of all be connected to J and K of the flip-flop number 1. And then the output of this flip-flop number 1 together with the external count enable should pass through AND gate and then drive the J and K of this one. And the output of this one also together with the output of this previous gate should pass through another AND gate to drive the J and K of the next flip-flop, and you continue. Now, what is the meaning of this? The meaning is that whenever the count is available, this J and K should be toggling, because the count is always 1. So whenever it is present, it will toggle, it will be changing. That is, with each clock pulse, the value of flip-flop number 1 should be toggling between 1 and 0. But for that same to happen to the second flip-flop, it means the enable count must be available and the output of this first flip-flop must also be 1, so that both of them will make this one to start toggling. And the same thing applies to the third one. You can see the JK of this one is driven by the output of this and then the output of our previous AND gate. What is this saying? It is saying that this output must be 1 and this output must be 1, as we know that our count enable is always equal to 1. So in essence, we are saying whichever clock pulse, the flip-flop number 1 is toggling, but the flip-flop number 2 will be toggling only when this lower flip-flop is equal to 1, and the next one should be toggling only when the both of these two are equal to 1. And to illustrate this, look at our binary sequence. You see, supposing we start from the 000, so when the next clock pulse come, this last bit should be 1. When the next one come, it should be 0. The next one will take it to 1, like this, which means this bit, the last one, is always toggling with each clock. But if you look at the second one, it can toggle only when the lower one is equal to 1. For instance, when this one is equal to 0, this one does not change. But when this one is equal to 1, this one immediately changes to 1. But when it is equal to 0, it remains 1, it didn't change. Then when it is equal to 1, it toggles, it changes to 0, it continues like this. For the last bit, for it to be toggling, all the lower bits must be equal to 0. For instance, if you look at this place, the lower bits here is only one of them that is 1, therefore it doesn't change. And here, if you look at it, only one of them is 1, therefore it doesn't change. But if you look at this, both these two are 1, 1, that is why this one toggle to 1. So this is how it operates. The next is the 3-bit down counter, and it has the same block diagram, logic diagram with the up counter. The only difference is that in the case of up counter, we take the output, the real output of the flip-flop, and pass it through the AND gate. But in the case of down counter, we are using Q prime instead of the real Q, so that it will be operating in the reverse direction. But you can see my external count enable drives the JQ of this first flip-flop, then the Q prime of this one together with this, they will drive the JQ of the next. Then the Q prime of this together with what comes out from this AND gate should drive this one. Because of using this Q prime, it will now be counting from up to down. And of course, this is how the sequence should be. We normally have a preset button that will set it to the maximum value. So it means whenever a clock pulse is applied, this least bit will now change. Another clock will change it, another one will change it, another one will change. But for this one to be changing, the lower one must be equal to 0 this time around. So you can see when this one is equal to 1, this doesn't change, but this one changes to 0, this change. When it is 1, it doesn't change, but when it changes to 0 again, this one changes. And the same thing applies. The last bit, which is the most significant bit, can only change when the lower bits are equal to 0. For instance, in this case, the 2 bits here are not both 0, therefore it remains 1. Here also only one of them is 0, doesn't change, but here all of them are 0, that is why it changes to 0. This is the 3-bit down counter. Then finally we look at the up-down counter, which is combination of up counter and down counter. And if you want to understand this one very clearly, this is the logic diagram, and for us to understand it, we need to remember the operation of our up counter and the down counter, because this one is the combination of two. For instance, let me illustrate. If you want to use this circuit as up counter, all you need to do is to apply logic 1 here. If you apply logic 1, then it will set it in up counting mode, and if this one is 1, it will come to this, but when that one comes to this inverter, it will make it 0. Because this is an AND gate, its output should be 0, which means here should be 0 here, so which means this arm is not operating. Okay, but when this one is equal to 1, yes, this one is now having one of its input equal to 1, which means it will drive this J and K, and the output of this J and K, as usual, that's the Q. The output, this Q, should now come together with my external pulse to this AND gate, and this AND gate will now drive the JK of this, and the real output Q should come together and the output to this to enter this OR gate and drive the JK of this. Exactly the operation of our up counter. But in a situation where we want to use it as a down counter, what we do is to apply logic 1 here and logic 0 here. So if here is logic 0, definitely output of my inverter should be 1, and I have 1 here, 1 1 will make this one to be equal to 1. So because of this, if this one is 1, you know, here JK should also be 1 1, and the output of this should come here. You can see we take the Q prime and pass it through this, as we did in the down counter. When this one comes here, it will go and drive the JK, and we take the Q prime and pass it to this one. So this is combination of the two. So as usual, I advise you to kindly take your time to revise this thing carefully, watch it and over, you will understand better. And if you still have any problem, you are free to contact me. This is the end of our part 2 of lecture 3 of CMEN405. Thank you very much.